This is the story of two of our newest missiles and their roles in today's preparedness.
The United States Army presents The Big Picture, an official report produced for the armed forces and the American people.
America's defense today, of necessity, is on land, on sea, and in the air. But its greatest threat will be from space. The intercontinental ballistic missile traveling above the atmosphere at speeds of almost 5 miles per second, destined for a target within our borders. The danger will be great, but we need not be helpless against it. An anti-ICBM missile is being developed to intercept and destroy it far from its intended target. For this missile, the United States Army looks to its Nike Zeus. Recent history attests to the age-old military principle that for every new offensive weapon, there can be a defense. In June 1944, the V-1 launched toward targets in Holland and England was a frightening development in World War II. A flying bomb carrying 1,000 pounds of explosive capable of vast destruction. Then Allied fighters and anti-aircraft batteries began to play a trump card of their own. Guiding the 90mm guns was the Army's new electronic fire control system. Based on new principles, it provided target data for the guns electronically. With experience, the score of hits began to rise. This very weapon system was based on principles that in our time has led to the development of America's first anti-aircraft guided missile, the Nike Ajax. Nike Ajax first for defense against conventional types of aircraft. Then to meet greater demands against supersonic jet aircraft, Nike Hercules. And now, in the space age, a potential answer to the threat of the ICBM, Nike Zeus. Technical direction for this program was assigned originally to the Army Rocket and Guided Missile Agency at Redstone Arsenal, Alabama. To execute the basic system concept in this program, the Army turned to the scientific resources of American industry. Time to think and to try, lead time. You cannot suddenly buy the long period of research that must precede final production. Nike Zeus is evolving out of our experience over the past 15 years. Its story began in 1945, when Army ordnance and industry combined to explore the possibilities of an anti-aircraft defense weapon capable of attacking high-speed, highly maneuverable bombers. In designing the Ajax system, a basic principle was employed, which was to greatly affect the design of Hercules and Zeus. All three missile systems have their electronic brains on the ground rather than in the missiles. After a missile is fired, the extensive machinery of guidance remains intact. Early in 1952, Ajax, armed for the first time with a warhead, was fired successfully. The same Army industry team was next called upon to produce a new missile to have a range more than 3 times greater than Ajax and the ability to carry a nuclear warhead. Radar had to be more powerful for the longer range of the missile. The Army Rocket and Guided Missile Agency required industry to develop a missile of greater speed, range, and explosive punch. Hercules was the answer. A system which has intercepted targets traveling faster than 2,000 miles an hour and balloon targets at extreme altitudes. Today, Hercules and Ajax are proven weapons, guarding our cities, homes, and factories. America's steady growth of experience acquired in producing these missiles has been essential in preparing us for a new challenge, an anti-missile system for the space age. Here is the concept of Nike Zeus. Far outside the atmosphere, radar beams endlessly sweeping the skies detect the oncoming missile. Information flashes to a defense center and then to a precision radar assigned to track the target. Zeus is timed to fire automatically to effect the intercept within range. The booster drops away. A missile track radar guides Nike Zeus toward its target. The sustainer motor is released. The final stage with its deadly warhead can be steered by a vectoring motor. When Zeus reaches the target, it will be detonated far enough away from the defended area to save it from damage. Early in the development program, many agencies concerned with training, logistics, development, and production were brought together, bringing to bear years of experience, assuring that the Nike Zeus program would remain on schedule. The Zeus is now far more than a theory. Today, in its research and development stage, the facilities and production methods of American industry are being actively employed. In the North Carolina plants of a large corporation, intricate computers and many other electronic system elements are being fabricated. As an example of nationwide participation, several major contractors are working on the target track radar. The antenna mount here is being assembled at Coffeyville, Kansas. Some large elements by a company in Milwaukee. A company in Detroit is producing the hydraulic drive, and a concern in La Mesa, California is fabricating the reflector assemblies. The combined efforts of these many companies is directed toward completing a Zeus test installation at White Sands Missile Range, where thorough evaluation of the 2 other members of the Nike family have already taken place. The site is being constructed by the Corps of Engineers. For the missile track radars to be installed here, an engineering company is fabricating antenna mounts. A major aircraft company has developed and constructed the acquisition radar antennas for the transmitter as well as the receiver. This transmitter generates the high-powered pulses which are reflected by objects in space to the receiving antenna. This early design stands some 8 stories high. For the target track radar, this high-powered transmitter has been developed. While work proceeds on the ground-based electronic system, a missile test firing program is already underway. A booster arrives for a scheduled firing. On another day, the final stage, which will include a guidance system, is checked. The motor will carry the warhead to the outer limits of the Earth's atmosphere. This booster generates almost 500,000 pounds of thrust. The test day has arrived. The testings about to be performed on this early model will answer numerous questions on the characteristics of the missile. Questions such as, will the missile withstand the intense heat generated? Can it be successfully launched from underground? At Kwajalein Atoll in the Central Pacific, construction for a complete Zeus test system is well underway. This system will be tested against Atlas ICBMs fired from Vandenberg Air Force Base in California. Integrating Nike Zeus with other elements in our defense complex is part of the defense planning which ensures the one-step-ahead concept. Nike Zeus is today moving ever forward to meet the challenge from the space above us. This is Pershing. The United States Army's new surface-to-surface, solid propellant ballistic missile. An Army industry team began developing Pershing in March 1958. At Cape Canaveral, less than 2 years later, this team test-fired the missile for the first time. The firing was a complete success. Numerous successes have followed. The Pershing weapon system is now in its advanced phases of research and development. This weapon's importance to our arsenal is clear. A demanding schedule has been established for its development. The efforts of thousands of people all over the United States are being carefully coordinated. The Army and industry are cooperating closely, relying on each other, working as a team. The result is that Pershing is right on schedule and will be in the field operational within a short time. The road between concept and reality is a long, difficult one which must be covered quickly. Long before the manufacture of even the earliest research and development missiles can begin, innumerable problems must be discussed and resolved. Decisions must be made. Some of our finest scientific minds have been brought to bear on pushing the development to meet the need for speed and accuracy of the ballistic missile. These men of science have played a vital role in missile research and development, and thus in the safety of our country. The weapon system exists first in terms of mathematics. Each mathematical aspect of the system must be figured precisely to the utmost degree of perfection. On this computer, the design of the missile is mathematically evaluated. Are the missile's rocket motors powerful enough? Is its guidance system accurate? Will its ballistic shell take flight stresses? These are the questions which the computer answers. Once designs are proved out, manufacture begins, often under the most demanding of conditions. This technician is manufacturing a component of the Pershing guidance system. Some of these parts are precise to within 10 millionths of an inch. They are assembled in a unique white room in individual cabinets filled with dust-free filtered air. Here, Pershing's 2 rocket motors are about to be tested in a captive firing. They will be fired just as if they were in flight. First, the first stage motor. When the first stage burns out, the missile would coast in unpowered flight for a few seconds. Then the second stage ignites, and the first stage drops away. At Holloman Air Force Base in New Mexico, other components are checked out in a sled test, which simulates conditions of both flight and impact. This sled is capable of attaining maximum speed at the point of impact. As in every test, the missile components are checked carefully. This performance on the ground will give a good indication of the missile's potential in the air. The test is about to begin. No matter how large or how small a test, the objectives are always the same: to make certain that the weapon system is as rugged, dependable, and mobile as possible. The Pershing missile and its support equipment are being developed and tested simultaneously. These vibration tests will ascertain whether or not the missile will be able to withstand the extreme stresses of actual aerial flight. Even in the earliest test firings, ground support equipment was available for launching the missile. This equipment takes the place of much of the special test gear required in other missile programs. Hundreds of thousands of dollars are saved. Developing the components simultaneously results in a program which is not impeded by equipment delays. During these early tests, widespread interest had already been generated by the possibilities of Pershing. In Germany, late in the summer of 1960, the United States Army held a special demonstration for senior officers of the NATO command. In this demonstration, the Army displayed the maneuverability of the missile carrier. The entire weapon system, including the missile and its communications and checkout equipment, is transported on 4 identical tracked vehicles. For NATO, the Army took the missile through a simulated emplacement, erection, and firing. This piece of equipment erecting Pershing for firing also carries the missile during travel. This equipment is the key to much of Pershing's mobility. These soldiers were able to take the weapon through its paces easily. illustrating the simplicity of Pershing in its operation. In tactical situations, the missile will be transported on 2 of the 4 tracked vehicles. The warhead and guidance unit carried on one, the rocket body and its motors on the other. The other 2 tracked vehicles will carry communications equipment and test and check out gear.